Let's ask question like why back to basics? Means to say it's all about like stressing simplicity and adherence to the fundamental principles. Like what is easy to see is what is easy to miss. And like as Albert Einstein has told, if you can't explain it simply, you don't understand well enough. So with that, let's straight away jump to the topic with few questions to test where we stand. Few questions to test where we stand. And like I have few more slides to probably means to say add few more questions as well. Let's ask this question. So here like you are seeing I1, that's the current flowing through the impedance Z1. I2, that's the current flowing through the impedance Z2. What's the total current I? Any answers? I1 is 4 amps, I2 is 3 amps. What's the total current I? It is only Z1 and Z2. There is no continuation here. It is only I1 and I2, Z1 and Z2. The side is open. Question, what is I? So means what say we tend to give an answer like means what say one is 4 amps and other one is 3 amps. So it is a 7 amps. Or few people put like root of 4 square plus 3 square and find out the answer as 5 amps. But unless otherwise, if we do not know what is R plus jX in Z1 and what is R2 plus jX2 in Z2, we will not be able to tell I. I is basically a vectorial sum of I1 and I2. So in order to find out I, we need the magnitude along with an angle. If they have given 4 angle 0, 3 angle 0, then the answer is 7. If they have given 4 angle 0 and 3 angle minus 90, then the angle, answer is like 5 angle minus 36.86 and so forth. So it's a vectorial sum. It is not direct sum. Why I am stressing this important point? Because most of the times when the people are trying to size the transformer or a diesel generator, manually validate the transformer sizing or the diesel generator sizing during the motor starting, they will be having the base load and they will be trying to add the starting current of the motor to check the overload capability of the transformer or a diesel generator. That time exactly this happens means was the existing load is at some power factor almost close to 0.8 or 0.9, and the motor which is going to start, the starting power factor of the motor, can you any idea like what could be the approximate starting power factor of the motor? It can vary from anywhere between 0.1 to 0.12 to 0.25 or 0.3. It will be in the range of 0.2. It can vary from 0.1 to 0.3. So means what's the existing loads are at a different power factor and the motor starting current will be at a different power factor. But people like means what's say generally add this currents directly, which means like 100 amps is the base current and probably motor current is 10 amps and taking 6 times the starting current 60 amps, they will directly add 100 plus 60 160 amps and say that the transformer is not capable or a diesel generator is not capable. Just to ensure that you are adding a vectorial sum when the power factor of the current or power factor of the loads are not equal or impedance X by R ratio is not equal. So ensure that you are adding always the vectorial sum. Looks like a very basics, but I have seen so many legends in probably amazing power system consulting companies directly adding this current with that current. Like in Excel, it is adding is quite simple and easy, right? But we forgetting a very small basics, but that probably changes the entire equation, which means they are concluding that the transformer is insufficient or the generator is insufficient. But in reality, that could be like more than enough. All right. So means whenever you have two different currents which are connected, loads which are connected in parallel, ensure that like you are adding always a vectorial sum, not a direct sum. Let's go probably deep into the topic. Maybe before going for that, like I generally like means what say going back to our YouTube channel once. So means what say if you want to maybe more and more basics, I have probably talked in depth with respect to the basics of circuit theory and how to relate that in power factor correction part 1. Kindly ensure that you don't miss this video. This gives like a quite lot of fundamentals and the application of that is covered in power factor correction part 2. Per unit calculations, let's address the first important question. Why do we need a per unit? 90% of the cases people tend to give an answer that simple, easy for a calculations, etc. Answer is not really. What I mean, it is not necessarily for a simplicity. Like now we have like quite a lot of sophisticated computers solving complex dynamic equations. So we do not really need a simplicity to probably our calculations. That's not the reason. That's not really the main reason. Right. So let's probably talk about this. Means what say I'm saying like 123 kV. What you have understood from this? I'm giving an actual number 123 kV. What do you have understood from this? I'm giving an actual measured voltage 123 kV. What do you have understood from this? We couldn't understand anything from this unless otherwise there is another additional information which is needed to support this. Actual measured voltage is 123 kV, but what's the rated voltage or nominal voltage of the system? Whether it is a 110 kV system or is it a 132 kV system? So hope you can easily understand what I'm trying to say. We basically need two important parameters to justify or make an inference or a conclusion. 110 kV is a rated voltage. 123 kV is the actual voltage which is available at this moment during live load conditions. So this precisely gives an inference that means 110 kV system, which is like over voltage by about a 10%. That makes some conclusions. Probably instead of this, I'm giving like my voltage is 1.1 per unit. I have never told what is the rated voltage, which is 110 kV. I have never told my actual voltage 121 kV or 123 kV, which I have never told. I'm just giving a per unit voltage. My voltage is 1.1 or 1.12 or 1.13. That's giving straight away in inference, irrespective of the magnitude. Irrespective of the magnitude, the per unit value straight away gives an inference. 1.1 per unit is an over voltage, 0.85 per unit or 0.93 per unit is an under voltage, 0.7 per unit loading is marginally loaded or 0.9 per unit loading is marginally loaded, 0.1% or 0.2 per unit loading is like lightly loaded. These are all giving us straight away messages, making an inference, then probably telling some two different numbers, right? Means if we go with an actual value, I need to tell two different values. One is an actual value and other one is a nominal value to make an inference or make a conclusion. But per unit value will straight away give some inferences. Probably let me probably put it like an advantage of giving the impedance in per unit for the transformer. Just an example I'm giving. If I am giving transformer impedance is, say, example 13.5 ohms, that doesn't really make any conclusion out of it. But instead, if I am saying my transformer impedance is 0.1 per unit, or 10% impedance per unit, 10%, it's just multiplication by 100, right? So this giving like three valuable informations. When I'm straight away saying 10% is my impedance or 0.1 per unit is my impedance for a transformer, it's giving like a straight away three important informations. What's the reactive power loss in the transformer when the transformer is fully loaded, which is 10%? What's the voltage drop in the transformer when the transformer is fully loaded, which is 10%? So you can relate such informations. What's the voltage drop? What's the losses? All these things just by means of when the impedance is in per unit, right? And it is also giving another important informations. More or less, what's the maximum theoretical possible short circuit value? 1 divided by 0.1 per unit, it's a 10 per unit, would be the maximum short circuit current on the LV winding. So this may not be possible. Such inferences you cannot really make it when the impedance is given as 13.5 ohms. And if 13.5 ohms is given, then you need to ask with respect to a transformer another important question. Whether this 13.5 ohms is referring to the HV winding or this 13.5 ohm is referring to the LV winding. And like this are not same. If the impedance is referred to the HV, the value will be different. And when the impedance is referred to the LV, the impedance is different. So Y per unit, with respect to the voltage and with respect to the equipment loading, this one number gives straight away inference. The second important of the per unit calculations means also you need not really convert the impedance from one side to the other side for the transformer. This is equal on the both the sides, and it directly gives some relatable informations like what's the reactive power loss, what is the voltage drop, what's the maximum short circuit current, etc. Now, there is another important aspect. Is that per unit new formula? Like, this is another important aspect, like which we might have studied in a college, but like we have missed across probably along the experience. That is like, if my transformer is like 80/100 MVA, 80 MVA on oil natural air natural and 100 MVA on oil natural air forced. If my impedance is 10% on oil natural air natural, what's the percentage impedance of the transformer in oil natural air forced? But question is like, you will not really test the transformer impedance at its rating probably you will be testing the transformer impedance at like some other values. Impedance value will not be the same. Means what, say 10% on 80 MVA and 10% on 100 MVA are not one and the same. And why it is important to convert one impedance from one MVA base to another MVA base, which you might be needed for multiple applications, because like you will be having multiple equipments in power systems. They have like individual ratings, and generally like all the transformers, when we say impedance we are specifically telling on that MVA rating of the transformer. And you will be having 100 MVA transformer, 50 MVA transformer, 25 MVA transformer, 2.5 MVA transformer. You need to align all the transformer impedances in same base MVA so that you can add it. You cannot add 10% impedance on 2.5 MVA and 10% impedance on 25 MVA directly without making this into a common MVA base. Z per unit new is equal to Z per unit volt into MVA new by MVA volt into base kV volt by base kV new the whole square. If you have a transformer, if the transformer rating is like 11 bar 6.9 or 33 bar 6.9, but that bus voltage on the LV side is 6.6, then probably means what, say percentage Z new when you are trying to convert into a new base MVA. Kindly remember this is that volt into base MVA new divided by base MVA volt into kV volt by kV new the whole square. So what I mean by this, when you are trying to convert the Z per unit from one MVA base to the other MVA base, you need to ensure that you are properly converting. And while converting from one MVA base to the other MVA base, it is just not base MVA. You need to check what is the base kV as well. Especially when your transformer no load voltage is differ from your bus voltage, this conversion is a bit tricky, and that's also a real reason why your short circuit currents will vary from the actual value what you are calculating in a manual way. What I mean by that, typically your transformer voltage will be like 11 bar 0.433, but the bus at which this transformer LV is connected is only a 415 volt 0.415 kV. So you need to be careful when you are using this impedance. Z per unit new is equal to Z per unit volt into kV volt by kV new the whole square into MVA new by MVA volt. Ensure that like you are using this equation properly to convert, and 10% on oil natural air natural, which is 80 MVA, will be like 12.5% on 100 MVA, which is oil natural air forced, if you apply this formula. So Z old is 10%, base new is 100 MVA, base old is 80 MVA. Assuming that the voltage bases are remains same, then Z new will be like 12.5% on 100 MVA. These are all really important, because few cases the manufacturer gives the impedance on like a different MVA ratings. You need to probably relate this. And this becomes like more important when it comes to three winding transformer. 99% of the cases people will make these mistakes, and the worst is when this three winding transformers will not have an equal rating, especially for like generator step up applications or some other applications. Maybe you will be having like three winding transformer with equal LV1 rating and LV2 rating for a variable frequency drive applications or solar plant applications. But that's not true for a gas turbine plus steam turbine using a common step up transformer. Even the voltage could be different, your rating could be different. So when you are using this impedance, you have to be very careful about like what's the base MVA, and you need to know how to convert this impedance from one base MVA to the other base MVA. And like three winding transformers, most of the times people will specify only one impedance, which is not really always right. For impedance of three winding transformer, you have to tell HV to LV1, HV to LV2, and LV1 to LV2. You need three impedances, and for all the three impedances, ask what's the base MVA. Ask the base MVA, which is really important. I mean, so say I have seen like there are eminent EPCs probably has selected the impedance and probably ordered the transformers, and probably at the end when the transformer is at site, then probably means for say what they have conveyed on the transformer impedance is on a different base MVA, whereas the manufacturer has, I mean, so say provided the transformer impedance on a different base MVA, which resulted in, I mean, to say huge short circuit current at LV, where this, I mean, so say air circuit breaker which is available for the solar inverter terminals are not sufficient. Then probably means to say they have to replace 100 air circuit breakers at site with a higher short circuit capacity. So what I mean, like impedance of the 3-winding transformer looks very simple, but please ensure that like you are getting 3 different impedances, HV to LV1, HV to LV2, LV1 to LV2. In addition to that, you ask specifically what's the base MVA. That's most important for all the 3 impedances. And LV1 and LV2 not necessarily has to be same. It might be same for a solar plant. It might be same for your VFD applications, but it is not necessarily same for a different applications. We will move on to the next. So what is Z value? If Z1 is 10 ohm and Z2 is 20 ohm and both are connected in series. Let's take this Z value. Like I have 2 impedances. Previously it is connected in parallel. Now I am connecting 2 impedances in series. Z1 is 10 ohms. Z2 is 20 ohms. Can you say what could be the total impedance? When we say it's a 10 ohm, it's an R+jX. Z2, when we say it is again R+jX, this Z1 could be like 10 plus J0. This could be pure resistance. Z2 could be like pure inductance, which means like 0 plus J20 or 20J. Then if you're adding Z1 plus Z2, it's again a vectorial sum. It's a vectorial sum. It's not an arithmetic sum. Z1 plus Z2 not necessarily has to be 30. Z1 plus Z2 will be 30 only when X by R ratio of the Z1 and Z2 are same, or power factor of this Z1 and Z2 are the same. If it is different, means was a total Z value will be different. You can add resistance with a resistance directly. You can add reactance with a reactance directly. You cannot add an impedance with an impedance directly. Impedance versus an impedance is always a vectorial sum, not an arithmetical sum. When we say 10 ohms or 20 ohms, that's the magnitude of it. You have to ask either angle or probably you have to ask it in R+jX format. To be honest, like if you ask this question, Z1 is 10 ohm, Z2 is 20 ohm, what's the Z value? Answer is unknown. Probably means to say you need to ask the angle, or probably means to say you have to ask that's in a vectorial form, or you have to ask it in a polar form, which is R+jX form. And short circuit calculation for a 2-winding transformers, I guess like I have already reserved a post. I mean to say I'm not really going to spend a lot of time there. We have a beautiful post which has given mathematically validated the ETAP results with the manual calculations, step-by-step procedure in a video, as well as like let's come to this video sorry, for a short circuit studies. When you're doing a manual calculation of short circuit studies, why your results could be different from the software. You might have missed a C factor, or you must have pre-fault voltage. When you're finding out the short circuit current, you have to be very clear whether you're following an IEC standard or an ANSI standard. If you're following an IEC standard, use a C factor. If you're following an ANSI standard, then use pre-fault voltage. Ask yourself a question: have you used impedance tolerance of a transformers and generators? As per IEC 60076, transformer tolerance will be like plus or minus 10% if the impedance is less than 10%, and impedance is more than 10%. Then the tolerance is plus or minus 7.5% at your nominal tap. Ask yourself whether the transformer is existing or proposed. If you are using a data sheet value, ensure always you are having a proper tolerance you are using for the transformer, which means like if the transformer impedance is 8% and the transformer is proposed, you need to use 8.8% impedance for load flow, motor starting, transient stability, harmonic analysis, etc. And you have to use 7.2% impedance for a short circuit studies. You have to use negative tolerance for a short circuit, and you have to use positive tolerance for all other studies. Ensure that you are using an impedance tolerance. And then like generator, I mean, so say as per the standard, the tolerance is plus or minus 20% on XC double dash. Most of the manufacturers will commit 15%. Ensure that you are using a tolerance for the transformer and generator while performing a short circuit study. If you are missing the tolerance at any time when the actual impedance comes in the transformer, that may result in a worse short circuit current than what you have calculated. So ensure that always you're using an impedance tolerance as per IEC 60076 for a transformer and IEC 6034 for a generator. Please don't add Z directly. Always add impedance vectorially. Use R+jX format or Z angle theta 1 plus Z2 angle theta 2. So add always a vectorial sum, not an arithmetic sum. Other important aspect, use impedance correction factor for a generator impedance and transformer impedance, which people generally neglect it. There is an impedance correction factor as per IEC K suffix T for a transformer, K suffix G for a generator, or K suffix S for system. So use the impedance correction factors, which is really essential. That results in change in the fault currents, and probably means for say you need to account the contribution from other sources like motors, which contribute for a very short time, and you need to include the source impedance, which means like you need to include the source short circuit MVA also, which generally reduces the short circuit current. So whenever you are doing the manual calculations, ensure all these key points, which is there in our YouTube channel in the short circuit video. And coming back to this video, means was this block, which is short circuit current calculations with the source impedance, with the transformer impedance. We have validated three-phase fault current, line to ground fault current, line to ground fault current, all this with an ETAP, as well as the results which we have matched. For a single line to ground fault, we have drawn the positive negative zero sequence, and we have matched the single line to ground fault current results. Then we have added probably means all the faults, line to line to ground fault, all those things. Then we have added a cable, we have added a motor, then we have matched the same thing. We have added the cable, we have added a motor. So what's the impact of the cable, what's the impact of the motor, all those things which we have validated. Never ever miss a block, never ever miss this block. Of course, it's probably time consuming block to go through, and if you want, ensure that you're going through this. And if you have any comments, feel free to post the comments in the bottom, and we will probably take up the questions there. Short circuit calculations with the distributed generations. This is another important aspect of for a short circuit study. When you have a distributed generation, when I say distributed generation, it could be like a rooftop solar, or a wind turbine generators, or a small biomass generators, etc. This again probably means to say create quite a lot of issues. One is with respect to the equipment loading, other one is with respect to the losses, but predominantly with respect to the short circuit current. If the distributed generation, again we need to ask whether it is an inverter based like solar inverters, or it is like machine based like maybe biomass or something like that. So you need to be a bit careful, and probably means for say one of the plant which I can say in a recent project what we are working on, means what say EPC has backed the order. When EPC is backing the order, the wind farm is of a type 4 full converter based wind turbine generator, and they have done the sizing calculation based on that, and they have backed the order. And the end user has changed from type 4 to type 3 later, and probably type 3 is a doubly fed induction generator. This doubly fed induction generator is not like a full converter based. It's probably means what say stator is directly connected. So the short circuit contribution of this doubly fed induction generator is comparatively more than the type 4 wind turbine generators. So whenever you are doing with some advanced technologies, kindly ensure that whenever they change in the type of wind turbine generators, you are revisiting your short circuit calculations. So short circuit after that, like means you might be having like a different busbar schemes, like low voltage systems you may be using single bus bar, medium voltage you may be using single bus bar with a bus coupler arrangement, and like at maybe some voltage level you will be using main and transfer. Some voltage levels you will be using two main and transfer. You may be using double bus bar scheme, double bus bar with a single breaker, double bus bar with a double breaker, 1.5 breaker scheme, ring main unit, mesh arrangements, like a different schemes. Right? I'm not really going to touch much on this, and probably this is an equivalent circuit of the transformer which you are aware, and equivalent circuit of the transmission line. So here, like we need to probably look at the equivalent circuit of the transformer and the transmission line with respect to different objectives. So equivalent circuit of the transformer will be with the resistance and reactance when you are using for load flow or short circuit studies or a motor starting study. But when you are using the transformer for lightning studies or switching studies, you need to probably means if you are studying the transfer of switching over voltage from HV winding to LV winding on the transformer, then probably means the way you have to model the equivalent circuit of the transformer is completely different. So means when you are asking an equivalent circuit of the transformer, before that, like what most importantly which you need to ask is like what's the study which you are performing. So nominal pi model might be sufficient for some studies. You may need like a detailed modeling of the transmission line using a distributed parameter might be needed for some studies, and even that may not be sufficient. You may need to go for like much more detailed modeling of a transmission line for like maybe example a lighting study. So before you are trying to conclude what's the equivalent circuit which is needed for a transformer or a transmission line, you need to ensure that what's the purpose of the study and why I am making the equivalent, rather than just simply projecting this as an equivalent circuit of the transformer or a transmission line.